Howdy, this is Jim Rutt. This is a continuation of my podcast with Lee Smolin. Another realist branch of the tree is Everett and the Multiverse. Could you tell us about that?
So one of the things about the Copenhagen interpretation is that it assumes that the world is divided into two parts. The quantum system, which is what we're trying to model using quantum mechanical ideas and mathematics, and the outside rest of the world, where the observers and the measuring instruments and the clocks and the rest of us live, which is assumed to be described by ordinary, that is, pre-quantum or Newtonian physics. And so Bohr and the Copenhagen people require us to always treat a quantum system as a small part of the universe and treat the rest of the universe as if quantum mechanics didn't apply to it, but Newtonian physics still apply. That is, in our part of the universe, the Newtonian part, there's no uncertainty. Everything always has a definite value independent of how you measure it and so forth. Well, one of the questions that became interesting during the 20th century as all this proceeded is cosmology. Because meanwhile, Einstein invented general relativity, and people began to apply it to models of the whole universe, to study things like the expanding universe as discovered by Hubble. And that's become quite a big and successful subject, modern cosmology. So what does that have to do with quantum mechanics? Well, if quantum mechanics can only apply to a part of the universe, you have a bridge, a gap there that's hard to bridge. And so Johnny Wheeler, who is one of the great visionaries of 20th century physics, used to ask himself and his students, could you devise a version of quantum mechanics that you could apply to the universe as a whole, where you wouldn't have to make this separation into the quantum world and the classical world? You'd somehow have to acknowledge, frankly, that the observer is part of the world and the world is one, which is a quantum world. So could you make a quantum mechanics which was a description of the universe as a whole? And this was a huge challenge. And my personal belief is that no, to make a theory of the whole universe, we have to go beyond quantum mechanics. That's part of the search for completion of quantum mechanics. But one of John Wheeler's students was Hugh Everett in the 1950s, came to a proposal about this. And the proposal was to remove from the formulation of quantum mechanics everything about measurement and probabilities and just leave an equation by which the wave propagates. The wave is taking the wave side of the wave-particle duality. There's a wave equation called the Schrödinger equation. And then there are other equations that describe measurement and probabilities for measurement. And Everett said, supposing we just take the theory to be given by the dynamics of the wave and we throw away the rest, can we make sense of that truncated version of the theory? And because there's no explicit mention of experimenter and observer, could we maybe apply this to the universe as a whole? Now, there are two problems with this. In fact, there are huge problems with it. But one of them is, what are you supposed to do with the fact that when you make a measurement, sometimes there's one outcome, sometimes there's another outcome. Sometimes if you have a particle in a ground state of an atom, an electron in the ground state of an atom, you ask, where is that electron? Sometimes it's on one side of the nuclei, sometimes it's on the other side of the nuclei, sometimes it's close, sometimes it's far. But there's always a definite outcome to your asking the question, where is the electron? So how does this theory of the wave, which doesn't mention anything about measurement or probability, deal with that? And Everett's proposal was radical and shocking. He said every time there would in the usual quantum mechanics be a choice like that, where there could be different outcomes, I'm going to postulate that the universe splits into different universes. And in each, there's a possible universe which actually exists for each possible outcome of the quantum experiment, of every quantum experiment. So every time in nature, the cat could be alive or dead, or the particle could be decayed or not, or any of these probabilistic things. There's a different version of reality. The reality is continually splitting into different versions, or as he called them, branches. And we as observers are splitting too, so that there are enormously large multiple number of copies of each of us and all of us in all of these different universes. It's completely insane.
For the listeners, I'm assuming that we're talking about a truly gargantuan number of universes, like every radioactive particle, when it splits or doesn't split in any instant of time, is presumably yet another fork in the multiverse.
Now, the story of this is that it became controversial. A lot of thinking was done about it. Hugh Everett himself left physics and went into defense work, being a physicist and engineer for defense contractors, and had apparently quite a successful career in that domain, and kept up with the debates, but never went back into science. But many people have thought about it. There are several questions which you have to address right away. One of them is, how do you account for the probabilities that we see in ordinary quantum mechanics? When we make experiments, we see the theory predicts that half the time the particle is decayed by now, and the other half the time it's not, and that varies as time goes on and more particles are decayed. So there's a lot that quantum mechanics predicts about probabilities. Where do they come from if the Everett proposal is true? Because in the Everett proposal, every one of these outcomes exists not with some probability, but with probability 1. Each exists with probability 1. And the only question is, what do you experience on the branch that this particular version of you that I'm talking to?
Doesn't seem to be a contradiction to me. I mean, if you go down the branches and you just happen to go on the branches of white, black, white, black, black, white, white, that's what you happen to see. And because all of our experiments don't happen simultaneously, I don't see a contradiction there.
There's not necessarily a contradiction, but you still have to ask the theory where the particular probabilities that quantum mechanics predicts come from.
The nature of the branching, then, essentially.
Yes. One way to say it is that you have to reproduce this rule that I was telling you about a few minutes ago. The probabilities are proportional to the square of the wave, which is called Born's rule. There are sort of two stages in the history of this. One of them is Everett, who wrote this in 1957, and a number of people since who attempted to make use of it. And this this has not been an area where I work directly, but I certainly know many of these people and admire many of them, even if I find the idea very unsettling and unconvincing. There's a kind of first stage where people finally realize that Everett didn't have all the answers and that the Everett theory, as described in his papers, is not adequate to address all the questions it must. And then there's a group of mainly philosophers, although they're led by one brilliant iconoclast, the physicist David Deutsch, who's somebody that I admire enormously, even as I disagree with him about so many things. I think he's a great scientist. And his books are very worth reading, very provocative. So David Deutsch and then a number of philosophers at Oxford University made a much more sophisticated version in which they connected these questions about probabilities in the Everett world to questions about how you make decisions given probabilistic knowledge of your circumstance, a branch of probability theory that has been developed and is applied in the investment world or in a number of other practical circumstances called decision theory. So it was David's brilliant idea to apply decision theory to this question. That is, if you were an observer in an Everett world, there are no probabilities, but you still have to make bets. And what wisdom guides the bet you make when you bet which branch you're going to be on, where the particle went left or the particle went right. And so this is a new part of the subject, and there are lots of ins and outs of it. So here's what I regret for the reader. So I wrote these two stages in the development of the theory became two chapters in my book, chapters 10 and 11. And I think I misjudged. And if somebody has tried to read them, I freely confess that I kind of misjudged how hard these things were. And probably we shouldn't have put them in a book meant for, as you put it, an intelligent but popular audience. But maybe the reader can decide. In any case, it's a fascinating subject. In the end, the answers are unknown. That is, the experts themselves are, as of this moment, highly divided as to whether real logical and mathematical sense can be made of how you pull out probabilities from this theory. And it's a fascinating story, and it's ongoing.
I'm going to throw out an interesting lunch conversation I had with Murray Gell-Mann once at the Santa Fe Institute. That was one of the joys of being a researcher there was you got to hang out with people like Murray and, just have random discussions. And I went down the quantum interpretations discussion with him one day and said, "Hey, Murray, what do you think?" And I realized he's written on this, but he gave me a shorthand answer, which I have not been able to find him ever putting in writing, which he called the as if many worlds interpretation. He said, "You know about Everett and his multiverse?" And I said, "Yeah." And he says, "Imagine Everett is right about the math, but by some magical mechanism, which we do not understand, only one of the worlds actually happens at each such branch." He says that was his best gut guess of the best interpretation out there.
That's interesting. I never heard him say that either. But Murray did write a number of papers on the interpretation of quantum mechanics, most of them with Jim Hartle, who was a good friend of his. And they espoused something that they called the consistent histories interpretation of quantum mechanics, which I suppose is something like what you just described. It's an Everett plus rule for when you can regard the world as real rather than just a fictional possibility.
He certainly seemed to be a realist. I mean, he would denounce people that, I remember him saying once, "Yeah, some people say if you don't look at the moon, it's not really there. That's ridiculous. The moon's always been there." So he would certainly seem to have been on the realist side of your realist, non-realist divide.
Jim Hartle was more adventurous in his anti-realism. He basically said realism, schmealism.